Hello and welcome to Calculus class. In this video, we are going to look at section 4.6, the natural logarithmic function, and how to integrate it. The bullet points are pretty straightforward. Use the log rule for integration to integrate a rational function. And we'll also integrate trigonometric functions. We still have a couple antiderivatives of the trig functions to take care of, and we'll see those in this section. So, the log rule for integration. Way back in chapter 2, we studied two differentiation rules for logarithms. The differentiation rule, the derivative of the natural log of x is 1 over x, produces the log rule from integration that we learned in 4.1. The differentiation rule, the derivative of natural log u is u prime over u. Remember, what we are logging becomes our denominator, and then the derivative goes right on top. Produces this integration rule. The antiderivative of 1 over u du is the natural log of u, don't forget the absolute value bars, plus c. And these are summarized below. So if it says something as simple as x to the first, the antiderivative of 1 over x is the natural log of x. Again, don't forget the bars and the plus c. And if that's not just x, if it's something a little more complicated, that would be 1 over u du, antiderives to natural log of the absolute value of u plus c. Or an easier way to think about this, if we move that du up into the numerator and just call it u prime, we're looking at u prime over u. The antiderivative of u prime over u is equal to the natural log of that denominator u, don't forget the bars, and plus c. So you're going to see a lot of this section. We are looking to take the integral they gave us and sort of force it into the form of u prime over u. Once we get it into u prime over u, the antiderivative is pretty simple. And what's this insight? The integrals in Theorem 419 right here are frequently tested on the AP exam. Oh, and here's how the book introduces that. Because du is u prime times dx, that second formula can be also written like this. U prime over u dx is natural log of u plus c. Now, this log rule presented in this section goes a long way to enable us to integrate rational functions, or functions that look like fractions. For instance, each of these can be integrated with the log rule. So here, example 1, 1 over 2x, 1 over 4x minus 1, example 2, x over x squared plus 1. So all of these different ones here can be integrated with the log rule. Sometimes the form is obvious. Sometimes we'll have to move some stuff around to get it in the form that's going to work for us. So here we go. Example number 1, nice slow pitch right over the plate. And I'm just going to copy the problem here. Antiderivative of 1 over 2x dx. Okay, so 1 over x, it's pretty close to one of the theorems we saw on the last page, but what's messing us up is this 2. 2 is a constant multiple, so let's pull it out in front of the integrands, or integral symbol. So since it was a 2 in the denominator, it will stay in the denominator, so that's a 1/2. And then we have 1 over x dx. Okay, so this part that I'm blocking off in blue ink, the antiderivative of 1 over x dx, well, that's right here. That's the natural log of the absolute of x plus c. So once we're in this form, u prime over u, our denominator is x. The derivative of x is right on top. So this one's ready to go. I'm going to bring along the 1/2. And then this antiderivative will turn into the natural log of that denominator. Don't forget the bars. And plus c. Now, if you're on the AP test and you get this answer, maybe it does not match everything on the multiple choice possibilities. Remember, when you're dealing with logs, this coefficient out front can be moved up and made into an exponent. So we could write this as the natural log of the absolute of x to the half plus c. Or if you don't like the half power, we could make that a radical. Natural log root of x plus c. Okay, example 2. Using the log rule with a change of variables. Now, when I look at this, the first thing I see is that it is a fraction, and I'm going to antiderive it. So the first thing I do, a little mental check, I look at my denominator u, in this case it's 4x minus 1, and hopefully I can find the derivative of that right upstairs in the numerator. If that's the case, then we're going to just antiderive natural log of the denominator. Now let me copy the problem here. So downstairs is 4x minus 1. Our numerator is a 1. So if I want to force it into the form of u prime over u, I look at my denominator 4x minus 1. What is the derivative of that? I want that derivative right upstairs. Well, the derivative of 4x minus 1 is 4. So I'm going to multiply my numerator by 4. And of course, to balance that, I'm going to put a 1/4 outside the integral sign. And now we are perfectly in u prime over u form. Our denominator is a function. The derivative of that denominator lies right upstairs in the numerator. So we are ready to antiderive. The 1/4 comes along. The rest of it is the natural log of our denominator. I'm going to put it in absolute value bars and then add my constant at the end, and we're done. And of course, we could move that 1/4 up and make that a 1/4 power, or we could put that under a 4th root if we so desired. All right, I think example 3 will be next, and there it is. Find the area of the region bounded by the graph of this, bounded by the x-axis and the line x is 3. So let's take a look at this graph. There it is, all in the first quadrant it looks like. So we're going to set up our integral. Now they did tell us here out to the line x is 3, and we can easily see here we're going to start accumulating area at x is 0, and we will work our way along till we get to 3. So those will be our upper and lower limits, 0 at the bottom, 3 at the top. And then we're going to put our function in here, x over x squared plus 1. And we'll give it a dx because we are going to antiderive with respect to the x variable. And let's see if this is in the form that we can use right away. I'm looking at my denominator, x squared plus 1. What's the derivative of x squared plus 1? Well, I need a 2x. So I've got the important part. The x is up there. So I'm going to put the 2 where I need it, and I'm going to balance that with a half out front. So here we are. We have u prime over u form, and we're ready to antiderive. So that'll be the natural log of the absolute value of the denominator, x squared plus 1. Now here we're not going to do a plus c because this is a definite integral. So we're going to evaluate that with the fundamental theorem from 0 to 3. Now at this point, if you notice, what we are logging, x squared plus 1, that's always going to be positive. Because when we square something, it's positive, and we add another 1, it's still going to be positive. So at this point, the bars are not necessary. We could turn them into parentheses if you wanted to. It's not going to hurt anything if you leave them as bars, though. So let's see. Let's do a little fundamental theorem. We've got our 1/2 out there, and I'm going to set up some empty parentheses in here. We'll fill up with our upper and lower limits. So let's see, of course, first the 3 is going to jump in. So 3 squared is 9. 9 plus 1 more is 10. So this becomes the natural log of 10. Minus 0 jumps in. 0 squared plus 1 is 1. So this becomes natural log of 1. Now hopefully you remember from previous classes or maybe even pre-calc, what is the natural log of 1? That's a good one to have memorized. Natural log of 1 is 0. So that's gone. So what we're left with is 1/2 of the natural log of 10. Or if you want to move the exponent up and make it a half power, you could write that as the natural log of the square root of 10. Let's turn that into a decimal. Either of these would turn into the decimal approximately 1.151. We could use the graph they provided to see if that answer is reasonable. If I look at this and kind of turn it into a rectangle like that, so the base is 3, the height is 0.4. If you multiply those, you get about 1.2, and that's pretty close to what we got. So I think we did okay. Alrighty, up next, example 4. This has got 4 parts, A, B, C, D. I'll just drag them out here one at a time. And of course, all of these are going to be rational expressions. They are going to look like a fraction. So the first thing I always do is check my u prime over u. So I'm looking at this denominator. That's my u, x cubed plus x. What's the derivative of x cubed plus x? Well, that would be 3x squared plus 1. And look at that. Our numerator is exactly perfectly the denominator's derivative. So this one is ready to rock and roll. The antiderivative will be the natural log of the absolute value of that denominator, x cubed plus x. And we got it in bars because it might be negative. We want to keep it positive. And we're going to add our plus c. Okay. Letter B. Okay, we got some trig functions here, but that's not going to scare us. It is a fraction. So let's look at that denominator, u, tan. What's the derivative of tan? Well, it just happens to be secant squared, which is right upstairs. That's our u prime. And we are ready to go. So let's antiderive that. It will be the natural log of the absolute value of our denominator, tan x. And we're going to add our constant of integration. And there we go. Another one that was ready right from the start. Now this one isn't going to be perfect, but it's an easy fix. So again, as soon as I see this rational expression, I'm going to do a quick check for u prime over u. My denominator, x squared plus 2x, is my u. What's the derivative of that? That would be 2x plus 2. Now look what we have up here. We're really close. We want 2x plus 2. So if I put a 2 here, that would distribute and give us the d, or the derivative in the numerator that we want. And of course, if we're going to multiply this by a 2, we have to balance by putting a half out front. So now we are in perfect form, u prime over u. So this half is going to come along for the ride. And then we're going to have the natural log of the absolute value of our denominator, x squared plus 2x. And of course, I'm going to put that in bars to keep it positive. And I'm going to add my constant of integration, plus c. All right. Letter D, one more to go here. It is a fraction. So let's check for u prime over u. Denominator, easy enough, 3x plus 2. Derivative of that would be 3. So to get our u prime up there where we need it, we're going to have to multiply our numerator by 3. And of course, to balance, we're going to do a 1/3 out front. So now we perfectly fit our format again, u prime over u. So this becomes 1/3 natural log of that denominator, 3x plus 2. And it's in absolute value bars. And of course, don't forget your plus c. Okay, let's see what example 5 holds for us. Ooh, integrals to which the log rule can be applied often appear in disguised form. For instance, when a rational function has a numerator of a degree greater than or equal to that of the denominator, we cannot be in u prime over u format, but division may reveal a form to which we can apply the log rule. So remember, maybe you asked in a previous class, when am I ever going to need polynomial long division? Well, buckle up. Here it comes. So we're looking here at example 5. I'm looking at my denominator. It is a function. I'll call it u. What's the derivative of x squared plus 1? Well, that would be 2x. And my numerator is not even close to 2x. So right now, as far as log integration goes, we're kind of stuck. But let's do a little polynomial long division. A little scratch work off to the side here. I am going to divide x squared plus 1 into x squared plus x plus 1. That's squared plus x plus 1. And I got to move this down a little bit. There we go. So let's see. I want to get rid of this positive x squared. I got to multiply this x squared by something to have it match. Well, that's easy enough. That's a 1. 1 times x squared is x squared. 1 times 1 is 1. And remember, now we are subtracting here. We're going to subtract this. So x squared minus x squared is nothing. X minus nothing is x. And 1 minus 1 is 0. So this x is our remainder. plus remainder x over x squared plus 1. So here, I'm not going to move this out of the way yet. Here's our original integral. We are going to rewrite that as the antiderivative of 1 plus x over x squared plus 1. So the original problem here in the book and what I just wrote here in black ink, these are exactly the same. They do look a little different, but in essence, they are the same because all we did is the division. So now let's see if we can derive each of these pieces separately. The first one is going to be no problem. The antiderivative of 1 with respect to x is just x plus. Now, let me move this over. I'll give it its own integral symbol. Denominator x squared plus 1, that is our denominator u. What is the derivative of that? Well, it would be 2x. So I need a 2, and I'm going to need a half to balance it, bring balance back to the integral. So now we are in the form. We're ready to go. Bring along your 1/2, and then this will antiderive to the natural log of. Now I'm not going to use bars because again we've got an x squared plus a 1. So that's always going to be positive. We can give the absolute value bars a break. So we have that, and we're not going to forget our constant of integration. Yeah, that's good enough. Again, with this half here, we could move that up and make it a half power or put it back under a square root. But I believe the book left it just like this. Okay, if I remember right, okay, I think this one, remember in section 4.5, where I made a big deal about the example 5u sub? We were setting up with our u substitution, and we had a little leftover x that we had to deal with. If I remember right, we're going to have to do the same with this one. Okay, so we are in the form of a fraction. X plus 1 quantity squared, 2x up top. Well, you know, usually we want our denominator to be a u. So let's let u equal that denominator, just what's in the parenthesis. So that's x plus 1. So let me derive this. Du dx would equal 1, and then we'd multiply both sides by the dx. So the du and the dx are interchangeable. So let's do those substitutions right now and see what this is going to look like. So u is x plus 1. Our denominator is now u squared. There we go. This dx is interchangeable with du. So there's a du. And we've done our substitutions, and what we're left with is an extra 2 times x. Okay, kind of just like we did in example 5 in the last section. We need to define x in terms of u, and we already did that right here. So if we go back here and solve for x, we're going to get x equals u minus 1. So I'm going to put a set of blue parentheses around this x, and we're going to take that x out and replace it with u minus 1. So I'll keep the 2 in red ink, and now that x is out, that's u minus 1. And we have a u squared downstairs in the denominator. And then there's our du. All right, we're getting close to where we can actually do the anti-deriving. See here. To make our lives a little easier, we could distribute the red 2, or, because it's a constant multiple, we can just drag it out here. There we go. All right, now let's do a little more algebra before we can actually anti-derive this. What sticks out to me, that denominator is a single term, u squared. Our numerator is in 2 different pieces, so let's break it up. Numerator u over denominator u squared minus numerator 1 over denominator u squared. And then the du applies to both of them. Okay, we are almost ready to anti-derive. A lot of work to get us there, to get us all set up. Let's do a little more simplifying with our algebra. That first term, u over u squared, well, we could factor out and cancel one of the u's from each. So now that is 1 over u. And then we're going to have minus, let's write this one as u to the negative 2. And then remember, this du applies to both of them. I guess I could have some grouping symbols around there. All right, it looks like we are ready to antiderive. Okay, 2 is a constant multiple. That'll come along for the ride. Now here we've got 1 over u, but remember this du is also attached to that. So we could write that as du over u, and it's in log form. We're ready to antiderive that one. So that's just going to become the natural log of u, whatever our denominator was. Now over here, this piece, we're not going to even use a log rule. Remember, when we have an exponent like this, when we antiderive, we are going to raise our exponent up 1 to -1 and divide by our new exponent -1. And we're going to also tack on our plus c. So we got that 2 there. Natural log of the absolute of u. This minus the negative, that's going to turn that to a positive. And then the u to the -1 is going to move downstairs. And now it's 1 over u to the first plus c. All right, let's, in the next step here, let's distribute the 2 and put our u sub back in. So we're going to distribute that 2 to each of these terms. And we're going to take out the u and put back in the x plus 1. So that's going to be 2 natural log quantity. Oop, I should have the bars on there. There we go. X plus 1. And then the 2 will distribute here. So now that's 2 up top over x plus 1. And when we distribute the 2 to the unknown constant, it's just still another unknown constant. Let's just call it c. There we go. Again, if you're taking the AP test, the multiple choice answers might not match this exactly. And one of the things we could do is move this 2 up and make it an exponent and make that a quantity squared. So natural log of x plus 1 quantity squared plus 2 over x plus 1 plus c. As you study the methods we see in examples 5 and 6, be aware that both methods involve rewriting a disguised integrand so it fits one or more of our basic formulas. Throughout the remaining sections of Chapter 4 and some in Chapter 7, much time will be devoted to integration techniques. Chapter 7 we're not going to get to. That would be a Calc 2 topic. To master these techniques, you must recognize the form-fitting nature of integration. In this sense, integration is not as nearly straightforward as deriving. Differentiation takes the form of, here's the question, what's the answer? Integration is more like, here's the answer, what was the question? Here are some guidelines we can use. 1, learn a basic list of integration formulas. By the end of the next section, we're going to have 20 basic rules. 2, find an integration formula that resembles all or maybe just a part of the integrand. And maybe by trial and error, find a choice of u that will make the integrand conform to the formula. When you cannot find a u sub that works, try altering the integrand. You might try applying a trig identity, multiplying and dividing by the same quantity, adding and subtracting the same quantity, or long division. Be creative. If you have access to computer software or a TI-89, use it. Just not on my test. Okay, here we go. When we look at this one, 1 over x ln of x. And of course, the first thing, it says solve this differential equation. So first thing we're going to do is move that dx over. So now it's on the other side. And if I antiderive the left side, the antiderivative of 1 dy is y equals. And then we're going to, of course, have to take the antiderivative of the other side, because that would only be fair. Now, when I look at this, my denominator is x times ln of x. If I assume that is my u, and I want to derive it to put it upstairs, I would have to use the product rule. And that product rule is not going to result in a 1. So we can use the log rule for integration on this, but what we have right now, it's disguised. We got to figure out what's going on here. Now, when we were doing some work in L'Hopital's rule, we've seen this technique a few times. It's going to come back here. So let me get this here. We're going to keep our natural log of x in the denominator, ln of x dx. This x here, down in the denominator, it's x over 1. If we bring it up to the numerator, we're going to flip it to its reciprocal, 1 over x. Aha! Look at that. Just that one simple algebraic maneuver, and we are now in u prime over u form. So if my denominator is u, what's the derivative of natural log x? Well, that's 1 over x. And that's my numerator here, 1 over x. So we are now in u prime over u form. We're ready to antiderive. Now watch this answer. I really like how this plays out. Remember, when we're in this form, our answer is going to be the natural log of the denominator. And what's our denominator? Another natural log. And don't forget your plus c. So this is the log of x plus c. Now we've antiderived sine and cos. In section 4.1, we looked at 6 trig integration rules, the 6 that correspond directly to the deriving rules. With the log rule, we can now complete the set of basic trig integration formulas. So many years ago, one of our math forefathers was pondering this question, the antiderivative of tan x dx. And remember, this log integration, we have to be in the form of a fraction. And right now, tangent does not look like a fraction. But if you remember pre-calc, I hope you had a good pre-calc teacher, tangent is also sine over cos. Aha! Now it is in the form of a fraction. Let's see if it fits our form. If my denominator is a function u, what is the derivative of cos? Well, that would be negative sine. And we're pretty close to negative sine there. If I just put a negative 1 here, I would have to balance that with a negative 1 out front. And now we are perfectly in u prime over u format. So our answer, we're going to bring along that negative, and it's going to be the natural log of the absolute value of just the denominator, cos x, and don't forget your plus c. So there's one to add to the old memory banks. What is the antiderivative of tangent? Negative natural log of cos plus c. And again, don't forget the bars. We can only log positive stuff, and cos can dip below the x-axis. So those bars are serving a pretty important purpose. Now, example 9 might be one of my favorite examples in all of calculus. It says here, example 8 used a trig identity to derive an integration rule for the tan function. The next example takes a rather unusual step, multiplying and dividing by the same quantity to derive an integration rule for the secant function. So again, remember, hundreds of years ago, somebody was pondering this question. What is the antiderivative of secant x? And I'm going to come down here and rewrite it as secant x over 1. So we are allowed to multiply the numerator and denominator by the same quantity. So somebody, many moons ago, did say, well, I'm going to multiply the numerator by secant x plus tan x. And if I multiply my numerator by that, I have to be fair and do the same thing to my denominator. So it looks like that. Now, let's distribute that secant I have here in black ink. So if we distribute, that's going to be secant times secant, which is secant squared x. And then if we distribute here, it's just going to be multiplied. That is going to be a secant x times tan x. And my denominator is 1 times that secant plus tan, so that's just going to stay kind of unchanged. Secant x plus tan x. All right. It sure looks like we're making this problem a lot more complicated and difficult, but we actually didn't. We are now in proper form. Let's double check. Our denominator is a function. Let's call it u. What is the derivative of secant? Well, that's secant times tan. What's the derivative of tangent? Well, that's secant squared. I mean, again, it looks kind of messy, but we are perfectly in the format of u prime over u. So our answer to this integral, or this antiderivative, is the natural log of the absolute value of our denominator plus c. And there it is. Again, I'd love to go back in time and have a conversation with the guy that figured that out. That's pretty neat how they multiplied through by that quantity. And it brought us perfectly to natural log integration form. All right, we just got a couple more to go here, it looks like. Well, first let's go over these 6 basic trig functions. So with the results of 8 and 9, we now have integration rules for sine, cos, tan, and secant. The integrals of the 6 basic trig functions are summarized below. So the antiderivative of sine, negative cos. Antiderivative of cos is sine. Antiderivative of tangent, negative natural log of cos, plus c. Antiderivative of cotan is ln of sine, plus c. Cosecant, this is the one we just did here, or excuse me, secant, the antiderivative of secant we just did. Natural log of absolute secant plus tan, plus c. And the antiderivative of cosecant is negative natural log cosecant plus cotan, plus c. So there are 6 integrals for our basic trig functions. Now in example 10, we're actually going to use or do a definite integral. So we have numbers now. We're going to have a fundamental theorem of calculus problem here. And when I'm looking at this one, let me just copy it down here. We're going to go from 0 to quarter pi, square root 1 plus tan squared. It does not look like a fraction. It's going to be kind of tricky to try to force it into that. But let's think back to pre-calc. 1 plus tan squared. 1 plus tan squared is a Pythagorean identity. And if you don't recall, 1 plus tan squared is the same as secant squared, x. Now, if we back up to the original, because we are adding 2 things under a radical, you cannot just square root the first thing, plus, and then square root the second thing. That is not 1 plus tan. That would be highly illegal, breaking many math rules. But we can turn 1 plus tan squared into secant squared. And now that it is a single term, we can apply the square root. Oops, where the heck did that come from? So the antiderivative of secant is natural log, absolute value, secant x plus tan x, and we will evaluate that from 0 to quarter pi. All right, I will use blue ink for the upper limit. The pi over 4 is going to jump in. So that's going to be the natural log, absolute value, secant of pi over 4, plus tan at pi over 4. And then the fundamental theorem of calculus says we subtract. And I'll use red ink for the lower limit, natural log of absolute, secant of 0 plus tan at 0. And I'll end my absolute value bars there. So let's see. Natural log of secant at pi over 4 is the reciprocal of cos at pi over 4. At pi over 4, cos is root 2 over 2. And if we flip that over, 2 over root 2, and we rationalize, it turns into a root of 2. Plus the tan at pi over 4, well, that's just 1. And I guess at this point, we could drop the bars if we wanted to, because the root of 2 and the 1 are both positive. They will stay positive. Minus natural log of. The secant at 0 is the flip of cos at 0. The cos at 0 is 1, and the reciprocal of 1 is 1. Plus, the tangent at 0 is just 0. So the first term, I'm just going to leave it like that. It is a very exact answer. Natural log of root 2 plus 1. And then we'll have minus. That's just going to be the natural log of 1. And I hope you've memorized that the natural log of 1 is 0. So that term just disappears. And there's our final answer. ln of root 2 plus 1. And as a decimal, let's figure as a decimal here, approximately 0.881. Now I see it says here numerical solution. Let me see what the book has to say. Ooh, oh my, why did they do this? Approximating the definite integral, they did a trapezoid rule with 4 trapezoids, and there was their delta x, pi over 16. Look at all those computations, and they come up with approximately 0.886. So you could do it numerically and come up with a pretty good estimate, but the work we did to get the exact answer wasn't too bad. I'd rather find the exact answer here than use the trapezoid rule. All right, are you ready for the last example? Grand finale. Finding an average value. Remember, the average value is different from other integrals because we're going to put a 1 over b minus a out front. 1 over b minus a. The a and the b are just from our upper and lower limits. So that's going to be 1 over, b is pi over 4, minus a, which is 0. So pi over 4 minus 0 is pi over 4. And when that's under a 1, we can just bring it up and flip it. So now it's 4 over pi. 4 over pi. So that'll be what takes this down to the average value. Now for the rest of it, we just want to find the area under the curve of tan x from 0 to quarter pi. Ooh, and I guess I'll put that on the integral symbol. 0 at the bottom, quarter pi up top. And let's give it a dx because we're anti-deriving with respect to x. All right, and we did just learn the antiderivative of tan. Good thing. So that antiderivative is the negative natural log absolute value cos of x. And we will evaluate that from 0 to a quarter pi. So I'm just going to get everything ready here with some empty parentheses. We've got our 4 over pi out there. And then in here, I'll use red ink for the upper limit. We'll put that in those parentheses. Minus, I'll use blue for the lower limit. That'll go in there. So let's see what happens. Back to red ink. Get over there. So the upper limit pi over 4 is going to jump in right here. That's going to be negative natural log, and I can drop the bars now because I know the cosine pi over 4 is positive. So that'll go in there. And then I'll back to blue ink. Our lower limit 0 jumps in. That will be negative natural log cos of 0. All right. Let's see here. Maybe have your unit circle ready if you don't have it all memorized yet. So we got our 4 over pi. We're going to save that till the very end. Ooh. I did notice in previous years before we did the fundamental theorem, I factored the negative out, but it shouldn't have a big difference on this. So here we've still got this negative, and then we're going to have the natural log of cosine pi over 4 is root 2 over 2. Root 2 over 2. And then this minus the negative, that's going to turn to a plus. And the cos at 0 is 1, so that's going to be natural log of 1. And we saw in the last example that natural log of 1 is 0. So let's see here. So now this term is going to turn into a 0, so I'm just going to scribble it out. So now we're back down to this, 4 over pi times this negative log. I would just sort of factor that negative out. It looks better as negative 4 over pi times the natural log of root 2 over 2. If we punch that in our calculator, let's get our decimal. That's approximately 0.4441. Now remember what this average value is. This is the height on the y-axis of the one perfect rectangle that would have the same area as the area under the curve. So here's our base, pi over 4. And if I block this off at the height we found there, the area in this blue rectangle is exactly the same as the area under that curve. We can see from the y-axis, yeah, we're pretty close to a half, about 0.4441. I think we hit the nail on the head. And I do believe that's the last example. Yeah, we'll just do some odd problems when I see you in class. I hope this video was helpful.